the models that contain this feature of negative feedback are thought to be widely applicable to a large number of biological problems, especially when it comes to not look at metabolites and proteins and messenger molecules in isolation, but when we study their interplay. So here's just an example of intracellular signaling, where the arrows, the brown and blue arrows, indicate some kind of feedback that is supposed to be there between important regulatory proteins in that cascade. And so we're not going to go into this complicated things, but I want to highlight that what we are going to say today deals with a single feedback loop, a single negative feedback loop. But typically in a biological system, if you look at it, there will be multiple nested, sometimes hierarchical, sometimes in parallel organized feedback loops. So things will be way more complicated in concert rather than in isolation. But of course, we use this to introduce how to work with these features. Our next slide, that should be up now, introduces the scheme of the model that we are going to deal with explicitly today. So it's the so-called Goodwin model. It was introduced by biologist Brian Goodwin in the early 60s in an attempt to account for the appearance of temporal structure in living systems, the self-organized appearance of temporal structure. And he found that one of the key features to generate temporal features, repetitiveness or rhythmic features, was negative feedback. So we take this model as it not quite in the way it's organized here, but you can see from the scheme that the idea is that there's a cascade of events where one depends on the other, and that the last member of the event, here called Z, has a feedback impact on the production of the first member of this cascade. So the way we are going to look at it is simplified from this to have our equations more manageable. Here's a scheme now shown. What we're going to look at is at a sequence of reactions involving only two components. So either two proteins or two metabolites or two signaling molecules, just say two substances, where the second substance acts as a regulator by inhibiting the production of the first. The model equations are at the center of the slide, in the middle highlighted in yellow. And this is the differential equation that we're going to look at, meaning that in contrast to the Goodwin model, we only deal with two variables. We only have two species here, but we have the delayed or the feedback by the second on the production of the first implemented just as in the original Goodwin model. What is the basic idea behind making a feedback negative? Well, I think, or maybe you can also imagine, the idea was that if you have a cascade that leads to the production of some final entity, then if there's too much of the final entity, there should be a feedback telling the beginning of the cascade to stop producing it. So I think that's the major idea, that there would be a information that goes to the beginning and saying, if there's too much of the final product of the cascade, please reduce the flow. And if there's too little of the final one, please increase the flow. So we're going to take this scheme, and we're doing it in two steps. First of all, we are going to look at only the feedback function, the term that starts here with the capital A. And only then we look at the two equations in completion as they are displayed here. So I take the slide away and let us start here. Rob will take over by guiding us, taking a look at the feedback inhibition function.
So hello everyone. So we're going to need a new script, because it's always good to start with a new script. I'm going to save this because we need to save it so we can run it onto the desktop, just as something called script inhibition. Okay. So if you recall the form of the feedback inhibition function, we needed three parameters. We needed a parameter, a km parameter, and a ki parameter, so the k constant of inhibition. So first of all, we need to define them, otherwise we can't do anything else. So I'm just going to set a as 1, km as 0.1, and ki as 0.1 as well. Okay. And then we need to define a function, which I'm going to call feedback inhibition 1. And the way we define this in MATLAB, if you recall, is using an @ symbol. And inside brackets after the @ symbol, we define the variables we're interested in applying that function to. So in this case, we're going to use x2. So that was the second variable. So we had x1 feeding into x2, and then x2 feeding back into x1. And so this is the feedback inhibition of x2 feeding back into x1, so we want it to be a function of x2. Okay, so our function of x2 is a over, open brackets, km plus ki times x2 to the power of n, and we're going to set n equal to 1 at the moment. Okay, so this was the definition of the feedback function we were given in the slides just before, but that's coded up as a MATLAB function, that whole line. Be nice to be able to plot this now. Okay. So we can use the fplot command to plot a function. So all we need to do is give it the name of our function, feedback inhibition 1. Tell it the limits, so I'm going to go for 0 and 2. And then that should run. Okay? Okay, that's interesting. But let's have a look what happens if I change this n parameter to 2, maybe, before we start doing anything else. So I'm going to copy that line. I'm going to paste it here. Let's change this function name to feedback inhibition 2, and change the value of n to 2. I need to do hold on to make sure that I keep this line in the new picture. And then I can do fplot and now call this new function feedback inhibition 2, give it the same limits, but of course we want this to be a different color, so I'm going to make it red, R for red. And let's run this. Okay, if I make that a bit bigger. Okay, so that's the result of running the feedback inhibition with 2 different values of n.
Okay, looks good to me. What can we interpret from this function? So we have on the horizontal axis, we have the amount of the regulatory substance, which is x2. And on the vertical axis, we have the output of this feedback function. So we can see they both start at the same value, meaning if there's nothing there, then they will be starting at the same value. But the way the function decay is different. So which one was which? What was the blue function?
The blue function was the n equals 1 function.
So if this exponent n is equal to 1, it starts with a fairly steep decrease, and then the slope decreases. It gets less and less steep until it finally goes, I think, towards 0 in the end. We would expect it to be asymptotically 0 if there's a very large amount of this substance present. So in contrast, the red curve, that's for the higher exponent, shows a different behavior, right? So it's a different form of this function.
So it starts higher, it starts greater, the inhibition is greater up until a point, and then it's lesser. Is that right?
Well, what it says is that the term here, which means that the production of x is higher, of x1 is higher initially, but later is lower. So initially the inhibition is a little bit less strong, and later it will be stronger. So
Okay.
that's due to it being a power of 2,
Yeah.
which is one that wins over the power being equal to 1.
And so if you increase the value of n, that effect will get even bigger.
That effect will be bigger and will get closer to what we call a step function.
Yeah.
So for very large n, we would have basically no decrease until this value of 1 here for our variable x2, but will be then very sharply decreased to a value very close to 0. And if somebody wants to test it, we can even recommend to test this. So
Okay.
I think that's what we can say. So the important thing is the more amount of variable x2 is present, the stronger is this effect of inhibition, the less we get out of this function. So let's now look what this means for the steady state or for the behavior of the whole model, because this is only part of the model. We now want to include everything else. How can we look at the full equation and find its steady states?
Okay, well, we can do this 2 ways. So I'm going to show you both ways now. So we've set up this function, this script file. Let me make it bigger so you can read the whole thing. Okay, just setting up the problem. So if you recall, these were our original systems of differential equations. So we have this term here, which was the term that we just saw. We've got some rate of decay at times x1, some rate of addition of x2 of rate x1, and some decay at rate x2. And then we've got the parameters, exactly the same parameters we used before. So I'm going to take those so that we've got them set up. And now we need to define equations equivalent to these ODEs. Okay. The first thing I'm going to do this algebraically, I'm going to define a function. So f at of x. So now this x, you may expect now is going to be a two-dimensional. It's going to have 2 elements inside it. So both x1 and x2 are going to be within x. So if we're outputting both x1 and x2 within x, we need our function to give us both equations for x1 and x2. So we can do that by saying it's a function. Our function returns a list here, so a vector. It's going to have 2 elements. The first one is going to be what we saw before, so x over kn plus ki times by x2 to the power of n. We need to set n as well, we need to remember to do that. Minus x1. Okay, so I haven't set n yet, so I'm going to set n here as well to be equal to 1. So that's the first line. If we then do comma, we are then able to write in the second equation, which is simply x1 minus x2. So I hope that makes sense. So we've got a function of a variable x, which has 2 elements. Therefore, we need to return 2 elements as well. So we return dx by dt of x1, sorry, d by dt of x1 and d by dt of x2. And then we can solve this equation by using the fsolve function. So what we get out from that is the steady state. We need to pass it the function f, and we need to give it the initial conditions. So where it starts off. So it's going to find the steady state, what happens at long time, where the system relaxes to. But we need to give it some guess about what we think the a sensible starting state is going to be. So let's just say we've got 1 unit of x1 and 1 unit of x2.
How do you actually choose these 2 values? How come you can pick 1, 1?
We could pick anything, couldn't we?
I think so. Yes, in this case, because we have no prior information, we just start with some arbitrary values and we see what happens. There are cases when this is a tricky thing and when actually it's required that we have prior knowledge about where to start this search for the steady state, but in this case it's in arbitrary start with some values that are just put in there, and it can lead to problems if you don't know your equation well. In this case, the equation is fairly simple, so in a larger model that may require more contemplation.
Of course, if we're looking at experimental results or modeling something that we're explicitly experimentally analyzing as well, then we may have experimental values for the initial conditions. So if you run this, okay, so it's told us that fsolve completed and it's given us two results. So this is the value of x1 and the value of x2. Okay, so the reason they're the same is because back here we had x1 minus x2, and now what the definition of a steady state is, it's when these two, when the x by dt, the x1 by dt equals 0 and the x2 by dt equals 0. So if x1 minus x2 equals 0, then x1 equals x2. And that's why the steady state value of x1 and the steady state value of x2 are equal.
Right, I can see that from the equation. So it also means that this is a special case here, which we get because the two rate constants are set equal to 1. Right, we don't multiply either variable with anything, so it means we assume a rate constant which is equal to 1. And that gives us this equality. So typically, if you have rate constants, they wouldn't be the same. I think biologically that would not make a lot of sense to have identical values. So if these values are different, then also the steady state values for the two variables will be different.
So that would be putting in a number either in front of this x1 or this x2 here, right? A multiple.
Exactly.
Okay, so we're quite interested in what happens as before when we change n to 2. So if I change n to 2 in our script file and then run it again, here we go, here's our new result. So here it's 2, 2. So what was that? So that's a smaller
right,
concentration.
Let's look at this. What does this mean? So the steady state value is the concentration that is assumed after all the transient behavior has died out. So it's the long-term asymptotic stable behavior. So what that means is that the higher the exponent, or we have now doubled the exponent, and that means the steady state value, which represents the concentration of the two species, has been lowered. So we have less amount present of either of the two components, and that means we can feel that the inhibition by the second component acts stronger to suppress the two concentrations. So we have the steady state less than if with other parameters same, if the exponent was equal to 1. So we could even study that quantitatively, but I think for us suffices that we can see this impact. We get different steady state values if the feedback function has different features as far as feedback inhibition is concerned.
Okay, so we've seen how to do this algebraically. We also want to show you how to do this symbolically as well. And the reason we might want to do this symbolically is, well, we'll show you in a second, because I'm not sure quite how fsolve works. Gerald, do you know exactly how fsolve works? I suspect what it could be doing is...
it's a Newton-Raphson iterative method, starting from one point, hopping a little bit, and then checking whether you get closer or farther away from a solution that doesn't change anymore, which is the steady state.
So it's doing it numerically, and that means it's putting in values at each stage. So what we'd actually like to do is get MATLAB to solve our equations for us, so using actual mathematics as opposed to using the computational approach. So we can do that by setting up the same problem but symbolically. So I'm going to close this script file, and I'm going to open a new one. Exactly the same as before, just with a few more bits of information. I'm going to also clear the results from that screen. Okay. So now we need to set up two symbolic variables, and the way we do that in MATLAB is with sims, and I'm going to call these x1 and x2, and these correspond, of course, to the same x1 and x2 as previously, but now they're two separate variables instead of one variable with two elements inside it. We need to set up some functions. Again, we need to do these separately now instead of just having, well, we don't need to necessarily, but we're going to do them separately now to have two equations for the symbolic differential equations here, rather than the one we had before. So now these are going to be variables. So I set a variable equal to this symbolic expression, and I'm also going to fill in the parameters now. We wouldn't need to necessarily, but it will make some of the analysis easier in a minute. So 1 over 0.1, which is the km, plus 0.1, which is the ki, times by x2 minus x1, and f2 is equal to x1 minus x2. So I hope you can see this is exactly the same equations as we had before, just we're telling MATLAB about them in a different way.
And you're assuming that the exponent n is equal to 1.
So we could do that explicitly by doing a power of 1, sorry, here.
Okay, perhaps you can see the power.
Then we need the solution, and we get that using the solve function. So solve, we give it an array with both f1 and f2 inside, and set that equal to 0. And so MATLAB knows that f1 equals 0 and f2 equals 0. Note the use of two equal signs to denote is equal to rather than set equal to.
So what's the difference between an equal and an equal?
So one is assignment. So here we can say we want f2 to be, we want to set it equal to x1 minus x2. And here we are saying, no, it is equal to, it is explicitly equal to.
Yeah, that's a logical equal.
So let's see what we get out from just running this script for now. Okay, so it's telling us our result from solve is two elements. So let's collect those. And I happen to know that these are the x1 steady states and the x2 steady states. So I'm going to call them x1 steady state and x2 steady state. And recall this is the notation for collecting two things from the output of solve. Okay? So I run that. Okay? Now again, we don't know what x1 SS is actually. We think it might be a number, but let's check that, shall we? So if I'm going to put this across just into the command line window, say what is x1 SS? Oh, it's two things, but they're quite complicated. So I'll go back to my script, and well, we want to know what x1 SS1 is to start off with, but this will give me, again, something that's quite complicated. So we can use this eval function to say, well, actually, no, I want to know what this is explicitly. I want you to evaluate this expression. But we can also pass it a list, and we can say, well, I want to know what x2 steady state is at the same time. So here, evaluate a list of things with x1 and x2 in. Sorry, 1. So if I just clear this for a second. So now evaluate the first element of x1 and the first element of x2. And they should correspond to the same steady state. Okay? That's the answer we got before.
So what do we see now? Let's not go too fast. What do we see? These two values are?
So that's the value of x1 at steady state and the value of x2 at steady state.
So we have, as we saw before algebraically, we can now see the value, sort of the concentration, the final concentration at stable steady state. So how come there is two values there in the first place?
So why did x1 have two values?
Yes.
Well, let's have a look what the other one is, shall we? So if I just copy that line and change 1 to 2 in both cases, and then run this again.
So that looks at the second element of either, of the first and the second variable.
So that's the steady state of our the one we know about, and it's the second one. It's negative.
So there is a second steady state, if we want to call it like this. So there's a second stable state that can be assumed and can be found. Why did we not find that in the algebraic way?
We just give it a guess for initial conditions.
Right. That had something to do with the guess for initial conditions. So why were we good when we chose 1, 1 for the initial conditions?
Well, I guess we stayed positive. So from the 1, 1, we hit the
Right.
positive solution.
Of course, a negative value doesn't make sense if we want to interpret this as a concentration. So what we have here is we find two steady states symbolically, but if we assume that concentrations have positive real values, then of course the second one doesn't make any sense and we can just discard it. And values for the first steady state, of course, happen to be the same as the one that we found algebraically.
I guess that's kind of interesting to point out that the mathematical model that we've built describes, well, effectively more than the biochemical model that we based it on. So we have mathematical results that don't mean anything in terms of biology, but that does mean that they're quite easy to discard because they don't mean anything sensible.
Right, that depends. We'll see. We might see examples where that also can be taken into account. And of course, there are many models that take into account other things than just concentrations, like voltages. Voltages can be both positive and negative, and in that case, the existence of two stable steady states might well mean something.
And I guess you can have the amount of change of something which could be negative if the change is negative, decreasing.
Yes.
So do be careful when throwing away results just because they're negative. But in this case, concentrations must be positive, and it doesn't mean anything to say that they're negative. So we can safely say that this is the only steady state in this system that makes any sense biologically.
Okay, Rob, could you show us the value when the exponent is higher, when it's, for example, 2, because we checked that before?
Okay, so F1, let's change that to 2. And then I'm just going to clear the screen so we know what we're getting. And if I run this, so the first value we got 2, 2, exactly as before. So that was the steady state we found before.
That was the steady state that we found algebraically for n equal to 2, which you have now also set. And here's another surprise. If we look at the second steady state, we like it maybe even less, because not only is it not a positive number,
it's imaginary too.
It's actually a complex number, so it has a real part which is -1, it has an imaginary part which is +2i. So for those who love complex numbers, that's wonderful, but we are not dealing with it when we want to get concentrations out of a model.
Yeah, no, that doesn't make much sense in terms of the biology. So, okay.
Okay, so that finishes our second exercise, the exercise that deals with the finding the solutions of the steady state and looking at those steady states numerically and symbolically. Shall I take briefly over?
Okay.
And we can come to the part that now deals with the simulation of the set of differential equations, where we'll get a little bit more out of it. Not just the steady states, but also the evolution into the steady state. So it's something that we want to do, and I'm going to do that by starting a new script file. And we want to develop a script file that allows us to look at the evolution as a time course. So for those who have done the previous sessions, for example, the model toggle switch, know how to do it. And we have actually prepared a model on our desktop. So if I, rather than writing it, if I just open it, and we'll have a look first at what this model looks like.
So this is a function file. So it begins with the word function.
Right. So this is not an executable script, but this is a function file that needs to be called. So it starts with function and then a name of the function and some assignments, and it ends with end to make it a round thing. And let's take a look what is inside.
So this dx by dt, so that's the final variable. That's what we want to come out of the function. That's what we want to set when we're running the function, correct?
These are the rates, exactly the rates that help us define how much of either substance will be winning or losing as time proceeds.
Then we've got the name of the function again. And so this needs to be the same as the name of the file.
That should ideally be the same as the file name, which it is in this case. So we called it model sub Goodwin sub S, and I meant the S to be short for simplified. So it's not the original Goodwin model, but it's a simplified version. And you remember we had only two variables.
So we have two input variables. We have t and x. So x is presumably x has two elements in, so x1 and x2, as before.
Right. The x variable collects all the variables of the model. So in this case, it will be 2, returning 2 values for the first and the second variable.
And this t's here, although we don't ever need to set this t explicitly because our function, it doesn't depend on t. This is here because the function we're going to use to call this function to simulate the model requires us to have a t as the first element. So
it's a special feature of the numerical integration method that we are using in MATLAB.
So if we have a function that we want to use the ODE45 function on, which we'll show you in a second, then we need the first element to be t, corresponds to time, and then the second corresponds to the vector of elements we're interested in, so x1, x2 in this case.
Right, so this is followed by a convention. Just some parameters are being specified, and they need to be given numerically because here we're not doing symbolic manipulation, but we're actually putting in values, and those values are being used for the simulation. And of course, at the core of this function is the definition of the differential equation. We have two equations, so if you just highlight the first one, the one that goes for the first element of our simple cascade of two elements. So the rate with which this first variable changes is according to our nonlinear feedback inhibition function. So it depends nonlinearly on the amount of the second variable, namely x2. And whether we take it to the exponent of 1 or 2 is up to us. You can see in the parameters that we start with a setting where n is equal to 1. And we complete it by this decay term in the end, and taken from the original idea of Goodwin, we then start our cascade with the production of the second from the first substance and the decay term of the second, both of which are linear first order terms with, for simplicity, rate a constant set equal to 1. And that completes it because we have now a way of calculating the xdt and of returning the actual values of how these concentrations change over time if we call this function.
So we can close that function file for now.
We can close it for now. We'll need it later. So how do we go about when we want to have a script?
So I need to save this script again first so we can run it. So I'm going to call this script sim for simulation, just onto the desktop. Okay. So we need to simulate the model. And as I said before, we need to use the ODE45 function. And so what the ODE45 does is it gives us back an array of time elements of x, which is the concentrations, so x1, x2. The function is ODE45, and then it takes a number of arguments. So the first thing it takes is the function we're interested in running.
Right, so that's sort of given by the name that we gave to our model file.
So we need to also prepend that by an @ symbol to tell it that it's a function. And then in this case, it was called model Goodwin S. So that's the name of the function as far as MATLAB's were. So we're using the @ symbol to tell it it's a function, and then the name of the function. Just going to move this down a few lines so you can see what I'm typing. Then I believe we need to give it the time, so the start and end time.
The time range.
So let's just say 0 to 10 for now. And then finally, the initial conditions. So the initial values of both x1 and x2. Should we say 0.1 and 0.1? Close the brackets. Okay.
Right, so we're going to do simulations with this setting here, and what we want to demonstrate is how the impact of the negative feedback changes the outcome of the simulation. So if I bring back our model, remember that in the nonlinear function, in the feedback inhibition function, there's a parameter called Ki, which determines the strength of the feedback inhibition. So for a given concentration of this variable x2 for the second substrate or second species, Ki determines how strongly will it impact on this production term for the first variable. So we have no feedback inhibition if Ki is equal to 0, right? That means we can just switch off the feedback inhibition. So let's start looking at the simulation, what this model, just a simple production chain, will look like if there's no such thing as a feedback loop. So in order to do this, I save the changes that I've just made, and we can then go back and run our simulation, knowing that we have no feedback inhibition in the first case.
So this is the simulation. This is the line that controls the simulation via the ordinary differential equation solver. Again, we gave it our function and the time range and the parameters, and outputted t and x. So t is the time, and x are these concentrations across the time. So if you want to plot, all we need to do is plot t, x. So if we run this, okay, so we're getting 2 lines, and they correspond to the 2 concentrations, correct?
Right, so which is which? Let's find out. If you have played with MATLAB, you know how to do it. An easy way without really checking is to go into the graphical user interface, into the plotting user interface, and it tells you that the first line is the top plot, the blue plot is the first variable.
So that's x1.
So that's our x1, and then obviously the green will be the x2. So the x1 starts to rises hyperbolically until it reaches a value of around 10. And let me change this slightly. No, that was not what I wanted to do. What was I going to do? I wanted to actually change the scale such that we can see the final variable a little bit better. Maybe make our lines thicker. So we can see that they both settle to the same value. As we said before, this is a special case where the rate constants are equal. And we can see that also there's nothing else but an increase until that final value is reached. What we note is that the second variable obviously follows the first, so it's delayed because it needs a certain amount of the first variable in order to produce sufficient amount or equivalent amount of the second variable. So that looks sigmoidal. As long as x1 is small, the second variable will also be small, but then it gradually catches up and they reach their steady state.
Okay.
Remember, that was the simulation of this simple chain model with no feedback inhibition. So let's compare what happens in the same model when we add the feedback inhibition.
Well, I want to keep this window open because I want to plot on here if we can. So what we need to do is go back to our function definition and change Ko back to 0.1.
Which was the value that we used previously.
I can close that now because I'm going to say keep that as that. Come back to our script file. If I just add hold on into the script, and run this again. So this is now running the model with the constant of inhibition being 0.1.
Okay, let's see the output.
Okay, let's make that a bit bigger again. And I'm going to make these lines a bit thicker so you can see.
Right, you make them even thicker so we can see which is from the second simulation. And already we can try a cautious interpretation. So we knew that the steady state value would be different, but we didn't know how it changes from 0 to first order feedback inhibition, but here we can see it numerically. So it shows that the initial part, say from 0 to a model time of 0.5 in units that need to be defined by the rate constants, looks very similar. So both variables start in a very similar way.
So right down at the far left end of the graph.
As time proceeds, there's a splitting up of the two curves, and we can see that the second simulation with the feedback inhibition consistently stays below the first, meaning that we can immediately see why we call this term feedback inhibition. Inhibition meaning that using this kind of feedback, we get lower values. And we remember that from the function, but now we can see how this translates into steady states. So this inhibition function now translates into decreased values of both steady states.
So we get this nice overshooting effect as well, where x1 increases above the steady state value. Previously, we just saw it increasing linearly to, well, not linearly, but monotonically, mathematically speaking, to this steady state, and now we see it overshoot and then come back down.
Okay, we see a little bit of an overshoot, which, if you remember in the materials, is something that we know from feedback to happen very frequently, that there is an adjustment that first rises above the steady state value and then returns to the steady state value. But if you check and play with this model in the sense that you tune parameters to different values, say for example, touching the A parameter and decreasing it and increasing it, you will find that this overshooting is not always there. It depends on specific parameter values. So for some values you will see it prominently, for some values you will see it hardly, and for some values it will not be there at all. So what I would like to see now, what does this output look like if we now increase the order of the feedback inhibition?
So to change it to x squared again, okay, well, we can open our model once more, change n to 2.
So it's now a different parameter. Previously we changed ki from 0 to 0.1, and now we change n from 1 to 2, meaning now we change the way the feedback inhibition function works.
Okay, close that. And if we run our script one more time, okay, getting a little bit.
I guess we need to maybe choose even different colors now.
Yep, so if so the blue line, shall we make that red? And the green line, I'll make purple.
Make it purple, yeah. And maybe you can take the first simulation away. Just take those and probably adjust the axis a little bit so that we can see it better. So now we can see it highlighted. It's easy to distinguish the two because we know that both variables that belong together end up at the same steady state. So if we now look at the impact of increasing the exponent, we can see that the red curve compared to the blue curve also overshoots, but it does so a little bit more steeply, and it reaches its maximum earlier.
Actually, as it comes down, we can see it overshoots again, so it goes slightly below the steady state after being quite considerably above until it increases again up to the steady state value.
Right, so what we can see here is that overshoot positively, overshoot negatively, and then reaching the steady state, which is actually something that we're not going to discuss today, but which is the start of where Brian Goodwin took off when he looked at these type of equations. Namely, he knew from engineering that the overshoots is something that indicates the possibility of seeing oscillatory behavior in such models. And before we make maybe a comment on this, so you can see here in the two settings where only the exponent was changed, that qualitatively we do not see much of a difference, but we see quantitative differences. Specifically, the steady state value of the second simulation with the higher exponent is below the first exponent, below the simulation with the exponent equal to 1, and that is what we expected from steady state analysis already. So we predicted that mathematically, and of course simulation should also follow the mathematics. It's actually the other way around. We use the numerical or symbolic calculation of the steady state to check whether the simulation gives the right output. So the mathematics has priority here. So that basically concludes our second exercise. So we have now looked at this specific function. We have studied the features of the feedback inhibition function. We have looked at a model that uses this function as a regulatory feature, as a feature to regulate. Say what we looked at was the steady state behavior of two species that are together organized in a cascade, in a production destruction cascade via this simple linear chain. And what this means is that we must expect things like overshoots and regulation of the steady state to be very much depending on the way the feedback loop is set up. So if you have looked at other models that are described in previous materials like the toggle switch, there are similar ways to control the output of one substance by the concentration of the other, and it's a very generic biological principle of organizing networks, organizing biological networks and controlling states and regulating states depending on some desired features. And in this case, is one thing that we find very frequently, for example, in all synthetic cascades, that the outcome of a cascade that leads to a product that is desired, say amino acids that we need for protein buildup or nucleotides that we need for DNA synthesis, that the cascades that lead to these end products have a feedback regulation by the product, by the end, the terminal substance in this cascade. So it's something widely found. And we have some understanding from our preliminary simulations what that might lead to. But a word of caution is at place, because once we go into networks, there's no intuitive way of predicting the outcome of the regulation, because then these things can be cross-linked. And if you remember our first slide, if I just bring it up again, if we have a model that involves multiple feedback regulatory features, like the brown arrows here, and maybe even a feedback that is positive, like the blue arrows, then there is no means of predicting straightforwardly whether the up or down of the steady state will in a simple way depend on the final product of the chain or no. It can be, but it can also be quite the opposite. And so in that case, it's mandatory that you set up your model according to the biological knowledge and do studies like steady state studies and simulation studies like the ones that we showed today. Okay. For those who have questions immediately, or MATLAB arrows shown up, if you have followed us and trying to do what we did here on the screen for you, you can use the chat function on the control panel to let us know. As this is not the case in this moment, I want to just use the last minutes of our session to show you one extension that is highly important for more realistic models. and it includes something that is maybe more difficult than what we did here, but just to give you the flavor of what this looked like. Namely, we do a model which is very similar to what we just did. It's two variables with two equations. One is x1, one is x2, and we have a nonlinear feedback function, and we have first order decay of the first variable. We have production and first order decay of the second variable. So it all looks very much the same, but there's a major difference here. And I'll highlight the difference by highlighting where it appears, namely, rather than assuming that the actual momentary concentration of the second variable decides how strong the feedback inhibition is, we now assume that this concentration of some prior time, of a previous moment in time, affects what happens to the inhibition. And the reason to do this is because if we go into, for example, signaling cascades, where one of the components is close to a membrane process and the second component may act close to the nucleus, that it actually might take some time until the feedback of something that's at the nucleus is being perceived at a membrane. So there's a diffusion process that needs to be taking place and that requires some time. So there's a delay. So what we have here, denoted by x sub delay, is that the concentration of the second substance, yes, acts as in feedback inhibition, but with some delay. And this forms a generic class of models which are called the delay models, or the models with explicit delay incorporated. And while I don't show you the details of how this works, I just want to show you that there are ways to do simulations here, namely that we can equally, as we did before, have a script that is set up to run this delay model, and we're going to use it to actually make a simulation of the same model as we had it before, but choosing different delay times.
I just wanted to add, it's a little bit more involved, but the key thing here is the use of this DDE23 function instead of the ODE45 that we used.
So we have substituted the solver, the function that performs the numerical simulation, with something novel, namely something called DDE23. And this is short for delay differential equations, and 223 refers to the order of the integration. And we're not going to go into any of the details here, but we want to highlight for you two features. First feature is, if you need to know what a certain variable was, how much it was at a previous time, you need to save a history. You need to keep track of what happened in the past, because the ODE45 solver only gives you present current time points, and you forget everything that happened previously. So this one, DDE23, remembers what happens in the past, and it does so with this history array where you can set up to keep track of this. And the second feature that we do is we can define the delay time. So in terms of the internal model time, we can define how long into the past we want to go, how long into the past we need the value of this, for example, second variable, in order to know how much will it affect our nonlinear feedback function. So if you just allow me to ignore all what is below this thing here. So we start with the simulation that actually does the simulation of the model with a delay set equal to 1. So that's in model time, whatever the units then are. And because that's in a different directory, I started to run here. So variable 1, which is plotted here in this first window, if you make it a little bit bigger. So what we can see with the moderately fairly short delay, we can see that the feature that we highlighted before, namely overshooting and undershooting, is now enhanced. And rather than having a quick approximation of the steady state, we have a slow approximation via an oscillatory output. But the oscillatory output is damped in the sense that the amplitude of the oscillation decreases over time. We have only plotted the first variable here, but you can trust us that the second variable also shows a damped oscillation and will reach the identical steady state. So this is one of the features where you can immediately guess, temporal structure, because the frequency of the oscillation can already be guessed from this few damped oscillation, from these few wiggles that we here see. If you want to calculate the frequency, you take the time it takes from one maximum to the next maximum and take the inverse one over this period, and then you have an estimate of the frequency of the oscillation. So we conclude the session today with doing a second simulation and just increasing the delay rather than having it 1 time units. We now have a much longer delay, 5 times as long if we put delay equal to 5. And if we just plot that in a window below the current one, we can see that the output is now different. Rather than having a damped oscillation, we can see that this is an oscillation with amplitude initially increasing. So the very first wiggle is extremely small on that scale that is plotted here. Second wiggle will be medium, and then finally increases to final values that are extremely high. So what does this mean? Not only does this model suppress and produce feedback inhibition, which we can see in the intermediate period, say between 40 and 47, that concentrations are low, but although there's permanent feedback inhibition, there can also be extremely large concentrations, but not always, only in a burst type fashion. So if you think of a signaling cascade, rather than having a signal on, either uninhibited or inhibited for all the time, which is what the steady state means, we have a burst of signal coming and then disappearing, and then after a specified time, another burst of the signal.